In my previous video about the method of weighted residuals, I told you that you basically have the full freedom of choosing the basis functions and the test functions slash weighting functions as you see fit. And this is what we're going to discuss in a little bit more detail in this video here, introducing a number of popular choices of basis and test functions and see what they basically mean. So the first approach is saying, okay, I went through a lot of trouble of finding a nice set of basis functions that incorporate the physics of the problem. I'm a little bit too lazy to figure out new testing functions, and I'm just going to say that my testing functions, my weighting functions, they're just the same as my basis functions. That's an approach you can take, and if you do that, you no longer have the generalized Galerkin method, which is another name for the method of weighted residuals, but you rather you have the regular Galerkin method, the so-called normal or vanilla, if you want, Galerkin method. So weighting functions equal to basis functions. What you can show in this case, which is not what we're going to do, is that in that case, the method has some variational properties with all of the nice advantages that we've discussed earlier. Okay, so this is one popular choice of basis slash weighting functions. Another choice is saying, okay, for my weighting functions, wj of x, I'm going to use a set of delta functions, a set of impulse functions centered around a certain number of points xj. Now pause the video and try and figure out, in that case, what it means for the residual to be orthogonal to these weighting functions. So we need to calculate the product, scalar product of the residual with our weighting function. And if we just simply say that for scalar product, we take an integral of the product of these two functions, the product of my residual and the product of my weighting function, which is a delta function in this case, and I integrate over the x, then by a well-known property of this guy here, you can basically say that this is r of xj. And if I put this equal to 0, what this particular choice of weighting functions means is that I'm asking that my residual vanishes at a certain number of predetermined points given by these points xj here. And this method also has a special name. This is called the point matching method for obvious purposes, for obvious reasons, right? And if you want to be a little bit more pedantic, you can also call this method the co-location method, which is like a Latinate way of saying the same thing as point matching. Okay, so this is using these delta functions as weighting functions. I remember these delta functions, they're very special functions, which are zero everywhere apart from at these points here xj in such a way that the integral over the function is equal to 1. But that's, of course, topic of another video. Okay, and then a final choice that you can make for your weighting functions is a little bit inspired by the first choice, but not saying like I'm going to use specifically the basis functions, but rather I'm going to use the basis functions after I have operated upon them by my linear operator L here. And this is also a very interesting choice because you can show in an exercise that this will result in the minimization of the total energy in your residual.